So what our research is about is, if I can put it in a simple term, is the molecular movie technology. I think this is a way of saying there are two magical words, molecule and a movie. Everybody loves watching movies, and then for me, particularly, if we can see how a molecule is dancing around, is vibrating, is rotating, is doing some kind of a magical transition that can give us a sense of a movie, then if we can capture it, and I think that's the wonderful part of our research. And the technique to do that is called the femtosecond Raman spectroscopy. This is an emergent structural dynamics technique that has been developed for the past, I would say, 10 years, maybe less than that. And I learned the technique when I was in UC Berkeley, and then I took it here in Oregon State, and then my team and I have spent a lot of time developing it, not only to use the technology to take all these molecular movies, but also to technically innovate and then try to develop the technology to be more feasible, to be more powerful, like you have a better gear to look at the process that is happening on a molecular time scale. I would say typically it's on femtosecond or picosecond time scale, which people may ask, what are those time scales? Those are extremely fast time scale. A femtosecond is a billionth of a millionth of a second, and a picosecond is 1,000 times of it. You might ask me why we care for femtosecond spectroscopy. The reason being that every molecule is vibrating on that time scale. So if we talk about a vibration, let's say two atoms are connected by a biochemical bond, and then it's doing this type of motion, and that period going from here to there and comes back is 20 femtosecond typically. So in order to capture those processes, you need to have a tool that is faster than that, and then that's why we have to develop this femtosecond vibrational spectroscopy to be able to capture those molecular movies. This is a fantastic question because we want to be in the zone. We want to do things that are relevant for everyday life. I mean, sure, all these physical chemists in the past have wonderful, they are really the geniuses in their own regard, and then they do these very super complicated problems, and sometimes they are very fundamental. But for us, because we are in the 21st century, I mean, we really want to do things that are relevant. It's going to keep our audience engaged. It's going to keep our graduate students and motivated. And then we only wanted to do things that can have an immediate and broad impact to some extent. So we picked the problems that are highly relevant for bioimaging, for example, that we study an emerging group of fluorescent protein biosensors that are derivatives of the GFP, which is a jellyfish green fluorescent protein that has won the Nobel Prize in 2008. And that is people thinking that, okay, that has revolutionized the molecular biology because we can finally genetically encode these fluorescent proteins into host cells, and then when you express those cells, it glows under a microscope. So you can actually see, how cancer metastasizes. You can see how things are moving around inside the cell. So we want to study this group of calcium sensing fluorescent proteins, and actually this is a fusion of the GFP, which is the green fluorescent protein, and then another unit which is called calmodulin, and then you fuse these things together and suddenly this thing becomes a calcium biosensor. So then having this biosensor, you can potentially use this tool to study neuroimaging. Right? Another aspect of our research is energy related. We have fantastic resources at Oregon State that has done material science, and then they have developed all these novel functional materials. So for instance, people like Professor Doc Kessler and then all these wonderful people at the center, they develop all these solution precursors that can potentially be transformed into a thin film. So this obviously is a nanocluster in water problem, and to study that kind of aqueous metal speciation problem, you need a technique that is capable of following that trajectory without the interference of the water, because the water is 55 molar, which is super concentrated. So IR technology, infrared technology doesn't really work because water has huge absorption peaks over there. So we use Raman. Raman, the water has literally no peak. So then you can actually focus on these solute peaks, which are these little bit nanoclusters, and it keeps growing and growing, and then eventually you can treat the solution and then lead to a thin film, which can have profound applications in corrosion prevention, in sustainable energy, in car coating, maybe even to put it on the Ford aluminum trucks. So these are the fantastic application potentials for these things. But if we go back to the origin of it, how can we understand those chemical transformations on the molecular time scale with the atomic precision, right? Essentially to capture the choreography of these atoms while chemistry is in action. This is really what motivates us and what puts our research in the zone. I used to say that I was so affiliated with the Ivory Tower because both of my parents are university teachers. So I was born on campus and I was brought up in a university setting, and I love the atmosphere that people are, collegiate, they talk to each other, they have great ideas, and then they encourage each other to elevate to new heights. So I think I've been doing well relatively in my academic life. I was at USTC, a great university at China, University of Science and Technology of China, and then I graduated. I came to the United States about, I would say, 14 years ago, and I first arrived in Philadelphia, and then I did my PhD at University of Pennsylvania. That was also Ivy League school. I enjoyed it a lot, and beyond academia, we can also do a lot of extracurriculum activities, which I think it's also helping myself to settle down in this culture. So I think what motivates me is that I have the passion and the drive to do the work, because being an academician sometimes means that you have to be relatively isolated and focus on your own stuff, and then try to do things that keeps yourself motivated. Because if you don't love what you do, I think this job is not that enjoyable, because sometimes you have to work long hours, sometimes you have to teach, you have to do research, you have to do committee service, and then there are tons of things that you have to do. But on the other hand, it's very fulfilling, because being an academician, not only you can push the research forward, you can do all these things that are having profound impacts on everyday lives of people, I hope. And also you can impact the next generation of young minds, because you are a teacher as well. So I really evaluate myself constantly and think that having this job is a privilege, not just something that I take very lightly. So having the opportunity to not only do research, publish all these papers, and then advance the field, and also teach students to think critically, to have these critical skills that is going to help them no matter where they go to academia or go to industry. So we are basically the support. So being the support is also a very fulfilling feeling, because we are helping other people, and then we are especially facilitating the growth of this country, of all these young people to become better people and become stronger people in the future. So this is part of the job, being a teacher and a scholar at the same time. This is a tricky question. Yes, I would say that people need to take breaks. You can't just work 24/7. But I have to say that being an assistant professor is not the easiest job in the world, because you do have all these things to balance it out. I particularly think that I want to have more time to do vacationing. I want to have more time to relax myself. I mean, maybe it's not. I want more time to sleep, but I think the balance is really in your mind, essentially, because if you are doing things that you don't like, then you feel that you are out of balance. But if you do things that you can you can feel passionate about, then you don't really question yourself, okay, what is the percentage of my work and what is percentage of my life? Because your work is your life. Okay? But on the other hand, I do think that people need to change their thinking from time to time. I remember Einstein used to say that the best way to relax is to find a different way to work. I mean, because I guess Einstein has so many things to work, so he has to balance himself out and then maybe play the violin or work on a physical problem and then go to a theater or something. For me, I think it's similar in the way that I like reading, I like movies, right? Not necessarily molecular movies, but all the movies, and listening to music and then traveling around. So I think doing those things will keep yourself balanced, and then at least you have a real touch of the world, and then to be always motivated to do the things. And then once you are done, you can give yourself a little bit of treat. Go to a fancy restaurant, go to visit a friend or family member. There are tons of things to keep yourself balanced. I would say that it's a big relief, and I'm happy that in a certain sense it's a recognition of the past about 4 years that we've established our lab here in Oregon State Chemistry. And I understand that this is a competitive award in this kind of a stringent funding situation. So we are very grateful that the National Science Foundation is willing to sponsor our work for the next 5 years, especially focusing on using the femtosecond stimulated Raman technology to to elucidate the fluorescence mechanisms of these emergent fluorescent protein biosensors. I have to say that this is a very satisfying journey as we are building our lab from scratch and get all these things done in a timely fashion and get all our papers disseminated through all these high-impact journals, and then for the world to appreciate and then maybe to draw some strengths from and take it to the next level. We can't do everything alone, so having this huge network of NSF is a plus, because now we have some critical resources to push our work in a systematical way to the next level, and also to collaborate with a lot of excellent people in different fields, from the protein engineering to the computational chemistry to the material science. So we have all these branches that we can tackle using the resources we have. And also this is a recognition for my group, all the graduate students and postdoc and undergraduate students who have contributed to our mission to make this project a success, and then also to be funded by NSF. So I think at this time, it's high time that we continue to work and continue to be innovative and continue to solve the most relevant problems in the current world.